a session that we did in the breakout session. Come up with your values first, then come up with the solutions second. So I'd now like to introduce Bob Wilkinson. Dr. Robert Wilkinson, or Bob as some of us have come to know in a very short 24-hour period, is the director of the Water Policy Program at the Graduate School, University of California in Santa Barbara. He's also a senior fellow with the Rocky Mountain Institute Research and Consulting since 1989. He's up in Canada fairly frequently working with CMHC, and I'll let him tell you a little bit about that before he starts his presentation.
Thanks. Maybe I should get the mic.
And you're live.
Okay. Well, you're all a very patient crowd, staying all the way through. So I'm going to go through, it's about a 2.5-hour talk on mathematics and modeling. Then there'll be a quiz. Actually, I have the real pleasure of working on a project for the Canadian government, for CMHC, that looks at the energy intensity of water. That is, all of the various inputs of energy into water systems, from wherever we take it out of systems, pump it out of the ground or extract it, all the way through to when it's discharged as wastewater or moves back into another loop if we reclaim it and reuse it. And the city that originally the government had in mind was Toronto, but it turns out there's so many interesting people doing good work in Vancouver that they switched it. So I'm doing the work in Vancouver to my great joy. So we're just getting started, and this will be for roughly the next year of process, as I'm learning to say correctly. My apologies for all my Americanized spelling on the slides, by the way. I'm missing extra E's and so forth. So what I want to run through is the Water Energy Nexus as an idea here and a research project in the context of what you're talking about. So these are the points I'll try to cover in 30 minutes or less, and then we'll take a little room for Q&A and wind it up. A little bit about this Water Energy Nexus, the linkages. Some questions about this continuum. How smooth is that ride? A little bit about energy intensity. I'm going to talk just briefly about climate change. I've been doing quite a bit of work on climate. That's one of the elements of the nexus is between energy and water. Impacts of climate change on water and impacts of energy use on climate change. Multiple benefits and integrated management. Some of these newer ideas, but maybe not that new ultimately, but trying to link water management with energy management in different places in the world. And I'll just mention right now, unless I forget, the city of Sydney is doing some very interesting work and some laws proposed in the last 2 weeks integrating energy management and water management with funds created to pay for it. Very interesting ideas worth looking at on the web. And the state of California is now formally integrating its energy planning with water planning. First time it's ever done a formal process of really trying to think through integrated management across the two. Beginning efforts, I'm sure there'll be a lot of lessons to be learned, but those are ones to watch. The idea of portfolio approaches that goes beyond diversity, but genuine portfolio theory, financial theory in water, and then finally towards the soft path. So quickly on the energy nexus, a few obvious points, but we're thinking about. These are key concerns to folks that are dealing with energy systems or water systems or both. I'm sure you're all dealing with the reliability issues of supply, cost issues, quality issues, and environmental impacts. These seem to be quite common across both. Both have an historic supply side orientation. That is, we've been focusing on getting enough energy, enough water, pretty much in a supply side mode for at least 100 years. Infrastructure at all levels is important. One of the things to recognize is that toilets and drip systems and laser leveling are as much infrastructure as dams and canals. So an expanded notion of what infrastructure is actually helpful when we think about how we allocate money and invest and solve our problems. We have huge end-use efficiency opportunities in all sectors, I think, anywhere in the world that I've been, working some in China, some in the former Soviet Union, in Africa, every place I've ever gone, there are big opportunities across the scale, even in the most efficient areas that I've seen. New technologies are changing our notions of optimal scale. That is, some of the filtering technologies in use are making local groundwater treatment from contaminated groundwater more cost effective than some of the interbasin transfer systems. So the technology is changing the game of scale. We've got market distortions and disconnections between pricing and cost. That is, the prices don't always reflect the full costs, certainly the environmental costs, but even the full operating and capital costs of systems. So there's some similarities. There's our sophisticated water policy process down south of the border. I suspect you might have some similar features up here. But water scarcity and some of the quality issues, some of the challenges, actually create opportunities for creative management and technology implementation strategies. And so that's part of what I want to talk about. 3 of the so-called new management, I have that in quotes because actually many people have been working on these for a long time, but integrated management, as I said, linking stormwater along with water and wastewater. City of Sydney, for example, now formally has a mandate to manage water, wastewater, and stormwater all in one authority. That's new, and that's a big shift in thinking, and it's, I think, a very good one. And now, as I said, bringing energy into that equation. Multiple benefit strategies, that is where we make an investment designed to achieve multiple benefits rather than just one. And I'll get into that a little bit more. And then this portfolio strategy approach, where you're really trying to understand reliability issues, quality issues, and invest in a mix that, with a real logic to it, that meets the reliability needs and meets needs for water quality for different types of end uses. So industrial processes may need a different kind of water quality, maybe treated effluent that's just great, as we're using for oil refineries and other uses in California. It's actually superior in some ways to other water supplies because it's very consistent and it's totally drought proof. You're always going to have it. And that means a lot to some of these big industrial operations. Now I'm going to question in a friendly way this continuum because it sounds like we're just going to move nice and smooth, but I'm going to suggest there may be bumps on the road. So watch out where you park. And there may be, you know, some ruts we fall into. We may get stuck in the mud in some of that. May even get bumps on the water. So I can't imagine how they got that one skewered. So there's in a fun way, thinking that this isn't as easy as we might like, but on the other hand, there are big opportunities. So we get energy from water, hydro facilities and so forth, and we use quite a bit of energy to supply, treat, and use water in the systems. Even when we have gravity feed of water supply, there's a lot of energy inputs into these systems. This is real data for one utility that I like because they have a whole variety. It's hard to read that, but the low left there, this is in kilowatt hours per acre foot. So the metric is energy units per water, is recycling. By the time you treat wastewater to legal discharge requirements, the marginal amount of energy to treat it one more step and then be able to use it is actually pretty small. The next one's groundwater in their case, and of course that varies due to depth and so forth. That's about 950. Ion exchange, that's a desalting for lightly contaminated salted water, say from dairy operations and so forth. Then they have a reverse osmosis, RO system for groundwater desalt, and that's coming in about 1700. What's interesting, those are the left 3, is then you get up to the existing systems we have in California, the Colorado River Aqueduct and the 2 branches of the state water project that are considered the conventional, and they're much more energy intensive, a lot more energy per unit of water to bring water in than to clean up and reuse a lot of the water that's already local, and that was a big surprise. By comparison, they don't have ocean desalt in this area, but ocean desalt's running now at about 4,400, and that's coming down, so it's interesting to kind of compare the extremes there. Energy intensity, or embodied energy, is the total amount of energy calculated on a whole system basis. That's from that extraction all the way through to the end, required for use of a given amount of water in a specific location. And this is what we'll be looking at for Canadian cities using Vancouver as a test case. And we're going to plot all of that through and then tie to that criteria, emissions, greenhouse gas emissions, other variables that one can derive from that to understand the benefit of some of the programs that you're just describing, the toilet retrofit programs and so forth. So here are each of the steps: the primary extraction, treatment and distribution, on-site water pumping, treatment and thermal, that's recirc in the building and heating and cooling and so forth, and then wastewater collection, and there's actually quite a bit of energy that goes into collecting and moving wastewater around before it's treated. It's not all gravity, unfortunately. So there's the same information in sort of a schematic. And the little extra loop there is for reuse. If water is treated and reused, it actually doesn't go back into this whole stream. It usually goes through a separate purple pipe system, is what the convention is for customer reuse, whether it's golf courses or flushing toilets. We're using it a lot now in high-rise buildings for toilet flushing, which is one of the major water uses in a big office building. It's perfectly good for that, industrial processes and so forth. This is interesting. This is going to vary by area, but this is just to show that for a sample city, this is California Energy Commission, it's a little dated, but I think the data is still pretty accurate. Water pumping is about 1/3, and wastewater treatment is about 1/4. So you put those two together, that's the majority of energy for a typical here's street lighting and building energy and so forth. Point here is that depending on the community, the number will change, but energy inputs for a community that's at the municipal level is non-trivial. A quick comment on climate change to tie that together. This is the plot for the last 150 years of global average temperature. You've probably seen this. If you go back 160,000 years to bring in some of the ice ages and the common and correct assertion, well, there's always been variability in climate. Yes, there has. But what we're getting now to at current levels and where we're headed is off the chart, and that's the big concern right now. I have worked quite a bit on climate change from the standpoint of the U.S. assessment of impacts and with Canadian scientists as well, and I can say that there's complete consensus that the Earth is in fact warming. The question is how fast, and some of the questions relate to what is it going to mean for precipitation, which will change. The current administration in the United States asked for a review from the National Academy of all this IPCC science, which is the Intergovernmental Panel on Climate Change, the international effort. They came back very quickly with a validation of that, and this is the quote from that very blunt statement. In fact, the temperatures are rising. Somehow, the current administration in the U.S. is scientifically challenged, so they were able to set this aside and not pay much attention to it. But having worked with folks across the board in the science community, but also the defense folks, the intelligence community, they're not only worried about this loss, for example, on the North Pole, they're worried about how thick that ice is, and it's on the order of half. And that's pretty sobering. So there are a lot of folks that are not, by any stretch, environmental activists that are very concerned about the rate of change, why this is happening, what's going on. So that's from 1979. So we're looking at just a couple of decades and a very substantial shift in polar ice, just as one example of climate change underway. This one hits home a little bit for you. That's over the last 50 years or so, and that's the deviation of temperature from the average, and we're looking at about a 2-degree rise. So you're in the 1 to 2 degree range in this particular area, and you can see there's a significant signal in the data for this whole region that's different actually than some other parts, and this actually is dropping. So a negative shift. Whatever that's due to, how much of it's anthropogenic and how much of it may be other things is second to it's happening. At least that's what the data is showing, and that's important. Now this is earlier spring flow, and I'm just going to bounce through this quickly, but this is up to 35 days earlier or later. So this is against whatever the average was in the past, over the past few decades, and what we're looking at is anywhere from about 5 to 15 days up to 35 days. And look at this amazing cluster right here. I'm not sure why, how much of that is just because there's better data here and gauging of this, but we're getting a pretty pronounced signal here of stretching out. Of course, what that is going to mean is differences in snowmelt and how much water is retained in systems versus how quickly it goes off. One last one here. This is observed data versus the modeling. From a modeling standpoint, that's a remarkable correlation, so it looks quite good. And what this is up to 80%, this 20 to 80 on the observations, changes either increase or decrease in snow water equivalent. And for water supply. Of course, that's very important. The reason you get some blue signal down here is that's the highest mountains. That's Mount Whitney, the highest in the lower 48 states in the U.S. And so they're above that line, but below a certain elevation, we're seeing a real shift here. And the models are actually frighteningly accurate on some of this. This is probably very similar to many of the water courses. This is the Sacramento River for 100 years, showing a continuous decline with bumps, but continuous decline in the spring runoff, and that's critical to water supply. So that's got the water management folks in California quite concerned. So we've kind of dropped the bomb on the climate issue, but maybe we'll pick it up in other ways. And I'm interested and intrigued that Canada's moving forward with some good policies. And part of that, I think, and keep this in mind, is getting credit in different ways, at least accounting for contributions you're making through water efficiency programs and so forth, because that does lead to significant greenhouse gas emission reductions. And that, that's, I think, this is personal now, how I think we're going to get from here to there is lots of small actions that really do add up, not one big silver bullet. So, multiple benefits quickly. With a focus on multiple benefits, we target various goals to be achieved through well-designed investments and policy strategies. For example, worried about water supply, so we do low-flow toilet retrofit programs. What are some of the other benefits that accrue by that program besides the water benefit?
Lower energy.
Lower energy for whatever treatment and pumping and so forth. Where does the water go when you flush?
Reduce wastewater.
So you got less wastewater treatment. Now, often we're facing capacity issues. We have to spend big bucks to expand wastewater treatment facilities. If you can forestall that or not even need to do it because you get that benefit through the reduction, now there's another capital benefit which can be quite significant. And then you get the air quality emissions reductions by reducing energy, so you begin to count all those up. Part of the argument there is if some of you are involved in that sort of program or moving into that, think hard about all those benefits and then look for co-funding. Are the wastewater folks chipping some money in? Are you doing this as a team approach because there are benefits that accrue to others? It makes sense, and we've got good examples of programs where there's co-funding and joint efforts for some of these efficiency investments because everybody wins. So here's the greenhouse gas emission point. I want to use a stormwater example. This is a blowout from poor management. But this is one of the trends we're seeing now in the U.S., but all over the world, trying to get water to basically percolate on-site wherever appropriate. So this is landscape use for parking areas, and actually the plants provide a tremendous service here. And of course they have to be climate appropriate wherever one is in the world. But the root structures make a huge difference in being able to wick the water down. Actually, a lot of treatment occurs of pet waste, and obviously sediment and so forth, but even car oil is quite effectively treated at the surface level in the soil, and then by some of the plant systems. They can be quite attractive, nice designs, but many communities have laws that prevent you from doing this because there's a requirement for curbs and so forth. So part of this is looking at what does it take to shift the policy strategies to be able to build like this. This is a retrofit on the Chesapeake Bay on the east coast of the U.S. And they just cut the curb and dug it out. That gets the first flush, all that sediment, huge pollution prevention benefits. Depending on where you are, that also then has infiltration benefits for groundwater recharge. And of course, if the storm is too big for that, you've got the overflow already. These are rain gardens. These are designed from scratch, very effective. This is just in. As that stuff grows up, you hardly notice it's there. The permeable paving systems to get the water to perk in right on the street. This is one of my favorites. This is a brand new facility. This is conventional concrete, and this is no rebar, pour about twice as thick, get rid of most of the fines, so you've got something like that popcorn that sticks together, and the water literally drops right through it. This is a thin section, but their sections are thick, and they love to go out there now. The maintenance guys for the facility, this is a water agency, were very skeptical. Didn't think this was going to work. Now they're the first ones to run out there with a bucket and demonstrate how they just pour it, it drops right through. So very effective stormwater. This is the EcoTrust building in Portland. Some of you have probably seen this, where there's a fairly sophisticated engineered system that's underneath this. This is now grown up so big you can hardly even see what's there. But that picks up all the stormwater flow. Daylighting, this is in Zurich. top and bottom pictures. So there's a pipe under the ground in the top photo, and then they've dug it up and daylighted the systems. You get recharge, you get the sunlight on the water, you get biological activity, and so on, improvement in water quality. So those are some design ideas for stormwater as one example of some of the strategies. Let me talk a little bit about another level now, technology options. This is what a reverse osmosis filter bank. How many have seen an RO system installed? Good. This is now used, of course, for wastewater reclaim, groundwater cleanup, ocean desalt. We're actually moving much more seriously than I had imagined in California on ocean desalt. And even though it's energy intensive, when one compares it against some of the alternatives in this portfolio kind of approach, there may be some merit in actually going this far for water supply, but it's certainly not cheap. There are a lot of very cheap options. You've got the waterless urinals that work very well, seeing those installed now, especially in high use areas. We've got them at the university, but in airports and all over. Low flow toilets, dual flush toilets. This is a big one. X-ray machines usually use once through cooling, so you save 90-something% of the water by going with a recirc cooling system for X-ray machines. Same with some other technologies. This is a spray valve. We're giving these away door to door to restaurants in California right now, often in restaurants that just runs continuously. So you're saving a huge amount of hot water energy as well as the water just by installing those. Of course, sometimes it takes teamwork with the technology. You have to look close. It took me a while to see what these guys are up to. I don't think that meets our safety requirements in California. Portfolio. This was just released last week. I'm on the state advisory group for the California Water Plan. We do a 5-year planning process. And this takes a little interpretation, but it's worth looking at. We looked at all the different options in California. This is water use efficiency, urban water use efficiency, conjunctive use groundwater. This is municipal reclaimed water. This is surface storage, new dams. Those are the biggest fights we have, of course. Agricultural water use efficiency, desalination, conveyance, it's not worth going into the nuances, and precipitation enhancement, which is really questionable, but cloud seeding is still in there. What's interesting is, where's California looking at getting its water, and this is out to 2030, so this 5-year plan, but it plans out decades. Where's all the water going to come from? It's all going to come from water use efficiency, some groundwater, and reclaimed. That's the big ones. Even if, the low end is kind of what's certain, and it goes up, and it's somewhat questionable on the upper ones, especially on these dams. But look what we're fighting over here, 0.05. It's 1/6 of what we expect to get from desalination at this point, and yet all of our political capital seems to be fighting over these dams. That's interesting. I think probably we're actually looking at the higher level on those first 3 as well, that the upper range is probably much more realistic, less so as you move to the right across those. So in a portfolio, one would want to invest perhaps a little more in reclaimed because it's highly reliable. So for your industrial processes and other purposes, you're solving several problems and you've got a reliable supply. This isn't to be overlooked as well. We've got a major public education campaign, and it's important to get the message out. This is the one I thought taking the message to the people is the creative advertising. A few slides on what this all adds up to. This is a decoupling of the population growth curve and the per capita water use. We had a pretty steady trend here back to 1950, and in the 1980s this decoupled. There's population growth continuing up. This is for the U.S. Total, and this is fairly current, but the per capita use is leveled off, and in fact I think that's going to start declining pretty seriously as a lot of the combination of rate structures, technology, techniques start kicking in for water supply. This is another interesting way to look at it. This is the withdrawals in the U.S., and you can see this incredible spike in the Southwest, and a lot of this is for irrigation of very thirsty crops in the desert. The spikes here, interestingly, are mostly for thermal power production, and a lot of that's returned in-stream flow, whereas a lot of this is actually consumptively used. So, a few points for the soft path. Amory Lovins, a guy that I've worked with since the 1970s, coined this soft path idea in 1976. in an article in Foreign Affairs that was the most reprinted article they'd ever published, and then wrote a book called Soft Energy Paths. A lot of the same ideas, with some nuances, are being adapted in the literature and the discussion for water. Basically, we're looking at integrated whole system approaches to management. We're looking at maximizing end-use water efficiency and trying to do it with quality that matches the purpose. Because we don't need the same quality water for everything. We don't need potable, high-quality tap water for many purposes. We're looking at tapping multiple benefits to maximize return on investment. Another way to say that is payback, but if we use the language of economics and the return on investment, a lot of the things that you're engaged in these programs have very good return on investment numbers. 20% return on investment. How many are making 20% on your money right now? I need to get your advice. If you try to pitch a 5-year payback project for funding, how likely is it you're going to get that? 5-year payback. How many people can sell 5-year payback in your institutions? Good, because mostly there's a threshold of 3. Oh, can't go beyond 3-year payback. Well, you think about it, 5-year payback's 20% ROI. That's very good if you've done good engineering and you're confident on the returns. Restoring and maintaining natural systems. This is one we're really just beginning to understand that restoring watersheds, restoring systems has huge benefits, including ROI, that need to be part of this. And then managing within the limits of systems. This is the limits to growth idea, but it's not just limits to growth. It's limits to systems, understanding them and figuring out how to manage within them, because when we don't, it gets very expensive. The consequences of managing outside of those limits and then running into that wall is not inconsequential. So my conclusions. This is one approach. We've kind of bury our heads. Whoops, too fast. This is another. And this, I think, really kind of sums up where we are in a lot of this. That, if we just step back and take a look at the opportunities, there may be a lot more, but we get ourselves like that, right up against the bars and don't really see what we can do. So water scarcity is a significant issue throughout the world. Droughts compound that challenge, if you know very well, having just gone through one. Energy intensity of water has become an important policy concern. In some areas, it's causing managers and decision makers to rethink water system design and management approaches. And I think that's an exciting opportunity on the upside. Water intensity of energy systems has become a significant concern in the context of water scarcity. We use a lot of water to run our energy systems consumptively. Most of our thermal systems use quite a bit of water. And so that's become an interesting issue to look at as we look forward. What are the alternatives in our energy infrastructure that would take some pressure off the water side of the equation? Population growth pressures pose significant challenge for both water and energy systems. I know you're facing that. I think most of the places that I've worked around the world, that is a major issue. We've got integrated management strategies that offer an opportunity and a tool to maximize these multiple benefits, including economic values and environmental restoration. A lot of the sustainability rhetoric, and I don't say that in a pejorative sense, but a lot of the language is this idea that one does not need to trade off in a zero-sum game economic values and environmental values. Actually, I think there are a lot of good examples coming out of water management that really show that you get economic benefits and environmental benefits, and indeed the social benefits, the equity issues, all in one package. But moving along this continuum, we do need to keep the pressure, so that's where the heat needs to go instead of up into the atmosphere, probably. And I'll close with my Winston Churchill quote: "People and nations behave wisely once they've exhausted all other alternatives." So we've probably done a pretty good job exhausting those alternatives, and now we're moving into this. That's my wrap, and hopefully we have some time for Q&A. How did I do on time?